So a slight correction I got to make. I made an error in the formulation of this problem. You now have the same line as before. Now, is it possible for me to find a plane that is parallel to this line? And well, if you think about it a bit, you think it is possible, but the question here is, this is a poorly worded question, which is I can find the plane parallel to LT. Well, it's not exactly one plane that's parallel to L, right? In this case, even if I want my plane to pass through this point here and to be parallel to L, there's several ways for me to do this, right? One way to do this is I could have a plane that contains both this point and this line L, right? That's certainly parallel to L. It also contains L. I could also have several different ways I could have this same scenario, right? I could, in essence, if you imagine L here to be the axis or some axis in this direction here, pretend this is like the z-axis, and this is some point, then I could really just take any point. Maybe I could start with a plane that contains this point here and also this axis. But then I could just start rotating this plane through the same direction axis at this point, P0. I could rotate it around, and I'm still going to get planes that are going to be parallel to L, but they're not going to contain L, and they're all different planes, right? But they all remain parallel to this line L. The upshot of this is I should have specified more information for you to find a single plane. All right. So here we go. Let me just make up a different line. Okay. Maybe we'll do part A first. Say here's a line, here's my point, and I want a plane that contains both. Right. So I could find some points on L. And then what do I do with the points on L? So remember, the goal here really you should rephrase this as, when you want to find the plane, you really want to find the normal to the plane, because then all your hard work's done. So how do I find a normal vector to this plane that contains both? What vectors do I have so far? So we know the direction vector for L, right? So direction vector for L. So let's call it V, and the direction vector, we read off the coefficients here, right? The direction vector is the coefficient in front of the t. In this case, it's 1, 3, 1. Okay, so we have one vector that we know has to be tangent, or has to lie along the plane, P, which means in particular, whatever normal that we get, it needs to be also perpendicular to this direction vector. What's another vector that might be lying along the plane? So one thing I could do is, let's say this is my vector V, just completely schematically. Well, I could draw another vector, artificially construct a vector, from any point P on this line and draw it towards my point off this line. So let's do, this is a displacement vector from P0 to P1. All right, that's done by subtracting the position of P0 from P1. So this is 3 minus 1, 0, I believe, which comes from taking P0 and subtracting off the point minus 1, 0, 2. So he actually does the opposite of this. But yeah, you could do either one, right? You could either do this or this, right? They both give you valid directions on. One's just a negative of the other. So P0, P1 is taking the point on this line. Let's take it at t equals 0. So you get minus 1, 0, and 2, and you subtract off 2, 1, 2, which is going to be negative, what Raphael just wrote down. So that's minus 3 plus 1 and 0. Okay, so I have these two directions that lie along the plane. Now what should I do with this? Right, so Ibrahim says, find the normal vector via the cross product. That's exactly right. And Mitsuka, yes, that's the value for t we choose is completely arbitrary, right? This works any point on this line. I could choose P1 to be here, which I could put like TB 100 and end up here, and then I could just have my green vector pointing this way, and that gets me another vector that points from P0 to any point on this line. So why is it not minus 1? Because I screwed up. That's the answer. Thanks. Thanks for the correction. This should be minus 1. Okay. Hopefully these are now right. Now to find the normal vector, we can call this the normal, and I could just do V cross P0 P1, right? So this could be V cross P0 P1. And what's that? Well, IJK, you put V in the first column, or first row rather, 1, 3, 1, and then your second vector, P0, P1 is -3, -1, 0, right? And this gets you 1, and then you get 3, or -3, -0, so that's -3. And then you get, what's K? K is -1, -9. So that's 9 - 1, that's 8. I hope that's correct. And now what should I do? I should just choose any single point that I want to be on this plane, which is P0. And I could just say the equation of the plane means 1 times x minus 3 times y plus 8 z is equal to some constant d. Now, because I want P0 to be on my point, I also have the fact that 1 times I now look at the coordinates of P0. That's 2, 1, 2. So I plug that in for 2, 1, 2 here. So it's 1 times 2 minus 3 times 1 plus 8 times 2, right? So what's that? That's 16 plus 18, or sorry, 16 plus 2, so that's 18 minus 3, so that's 15. So this means that D is equal to 15. We're reading off this now. So this is x minus 3y plus 8z is equal to 15. This is part A. Now for part B, we now have a plane parallel to L again. But now we want to contain a point P0 and another point 0, 2, 5 that's off of this line. Presumably, you could check that on this line here. If you want x to be 0, then t has to be +1. But then if t is +1, then on this line you're at y is equal to 3, and this is at 2. So this point is definitively not on this line. This plane is also very clearly not 2, 1, 2 because the numbers are different. So here's the situation. We have a line as before, and now we have P0, and let's say another point I'll call, let's say P1 is equal to 0, 2, 5. These are just floating in space. I don't have the coordinates down correctly, but the situation here is I now want a plane P, right, that contains both P0 and P1. I mean, P0 and P1 are off this line, but I do want P to be parallel to L. So in this scenario, how might I construct a normal vector to P schematically? I once again still have, one useful thing I have is perhaps I still have the direction vector V for this line. And I know that if I have a normal vector to my plane and my plane is parallel to L, then certainly that means you could imagine dragging and moving this orange vector V downwards in the way I drew this to lie along this plane P. I know that the normal vector to P must certainly be normal to V as well. It must be orthogonal to V, which means that it makes, its dot product with V is 0. So V is certainly at right angles to my normal vector to P. How might I get another vector to help me out? One way I could do this is I could find the direction vector from P0 to P1. I could artificially construct this now. And then I take P0, P1 to V, and then I take the cross product, and that could get me a normal vector to my plane. So I wanted to write V cross P0, P1 to keep it consistent here, but I guess the way I drew the orientation of these vectors, it has to be P0, P1 cross V in this scenario. Okay, so I'm crossing this with that, so it looks like that. All right, so that's the strategy here, and that gets me a normal vector to the plane, to a normal vector to this plane. And so we could do the computations. Once again, let me write down V as before is equal to 1, 3, 1, and P0, P1 is going to be equal to, well, P1 is 0, 2, 5, and P0 is 2, 1, 2. And so this is going to be equal to -2, 1, and 3. And so what do we have? We have, well, okay, so I drew the diagram P0, P1 cross V. I'm just going to do V cross P0, P1 here. It doesn't really matter. So let's do V cross P0, P1. That's going to be equal to, I didn't make this easy for myself. So this is 3 minus, or maybe I did. No, this is 9 minus 1, so that's 8. And I'll address the question in chat in 1 second. So this is 9 minus 1, which is 8. And then you have -2 minus 3, that's -5. And then you have, so the last one is 1 plus 6, which is 7. All right. So there's a good point here. In this case, could it be that P0, P1 and the direction vector of L are parallel and the cross product is non-existent? Yes, it's possible, which means, so that's a situation where you have two lines that are parallel to each other, in essence. If P0 and P1 were just pointing the same direction as V, just a multiple of it, then that means that you have the line through P0, P1 is going to be a line that's parallel to this line here. And then you could have a plane that is, you're now asking to find a plane through one line and not the other line. And so that takes some work. Maybe we could do that as another example after this. Let's complete this. So assuming I got this cross product, right? This is 8 minus 5, 7. So your equation for this plane is going to be 8x minus 5y plus 7z is equal to some constant d. And now you just want to identify a point that's on this plane, right? So in this case, 0, 2, 5 is certainly a point on this plane. And so I could plug in, right? P0, so P1 is 0, 2, 5 must satisfy this equation. So this means that when we plug this in, 8 times 0 minus 10 plus 25, that's 5. 7 times 5, 35. Well, that's 25. Must be equal to d. So this means that your equation here is 8x minus 5y plus 7z is equal to 25. Suppose now take P0, P1, same as above. So the vector P0, P1 is now equal to what we calculated here. It's minus 2, 1, 3. All right. Suppose L is a line given to you by x, y, z. It's equal to minus 2t, t, and let's make sure it doesn't go through any of our points, 3t. Okay, so this is a line with a direction vector exactly the same as our displacement vector P0, P1. I now have a line here as before, well, a similar thing as before, but this is now my L with direction vector V is equal to minus 2, 1, 3. And then I have 2 points here, P0 and P1, which are off this line, but they also share the same direction vector. They're parallel to each other. And how many planes go through this? And we have some idea here. Umara says multiple, Ibrahim agrees. So in this case, right, if our plane contains P0, P1, right, then it's always going to be parallel to V. Because in this case, well, if I have a dot product, one way to see this is if our plane contains, right, P0, P1, then certainly whatever normal vector is to this, it's also going to be normal it's also going to be normal to the point, to the vector V. Any normal vector to P0, P1, the displacement P0, P1, is also going to be normal to V. And there is now a circle of directions, right, that is normal to P0, P1. I could tilt this plane in like a circle of directions around this axis and still get a plane that is between P0, P1 or that contains P0, P1. They're all different, but they all satisfy the fact that they contain P0, P1 and are parallel. So in this case, then there are infinitely many through that contain P0, P1 and parallel to L. And let's see why that's true. And this goes back to the previous idea brought up in chat, which was let's look at this normal vector to the plane. So we need to be normal to V, which in this case is also equal to P0, P1. And so you end up setting the following. So let's suppose let n, the normal, have coefficients a, b, c. So you need to solve a, b, c dotted with the displacement vector, which in this case, P0, P1 is the same as V. It's minus 2, 1, 3, must be equal to 0. All right, so we could be sort of lackadaisical about this. So in this case, this gets you the single equation minus 2a plus b plus 3c is equal to 0. If you've taken any linear algebra or seen this before, then this is a underdetermined equation, right? You have the fact that you have a single equation here and 3 unknowns, not very good. We do know one thing, n cannot be the 0 vector, right? You want n to be an orthogonal, a normal vector. That means this dotted with this vector is 0, but this itself is not 0. Otherwise, that's pretty useless for our plane. So at least one of these coefficients are going to be non-zero. So you can make a simplification to this. You guys just, for example, set, so this is This is 0. You could assume, let's say C is non-zero, divide it out, right? So divide both, or just set C to be equal to 1, say. You could do minus 2a plus b plus 3, or you could set it to 0 if you want, but minus 2a plus b plus 3 is equal to 0. And then so you get the fact that b is equal to 2a minus 3. So n could be equal to a, 2a minus 3, and say 1 if you want. And so you get infinitely many planes, right? This, you could have, for a particular a, your normal vector might point here, another one might point here, another one might point here, depending on how you vary a. And each of that is going to get you a plane that contains, that is parallel to this line here. And to make sure that the plane contains P0, 0, and P1, you just got to make sure it contains P0. So let's say P0 has coordinates, P0 has coordinates 2, 1, 2. So once again, you have a normal vector here. It's a, 2a minus 3, 1 dotted with 2, 1, 2. And this is equal to, what's that? That's 2a plus 2a minus 3 minus 2, plus 2. That's 4a plus 4 minus 3. Okay, so this means that the equation ax, or the plane given to you by ax plus 2a minus 3 y plus z is equal to 4a plus 4 minus 3. This is a family of planes containing P0 and P1 parallel to the line L. Oh, is it 4a minus 1? Sorry, guys. As you can see, it's a weird day today. So this 4a minus 1 is the constant here. So, okay, let me just scroll back up. So again, she says, why can we set C as 1? That's just to narrow it down. So the reasoning was basically, okay, so I know at least, this is a very underdetermined system. There's a lot of solutions to this thing. It's not unique because there are 3 unknowns and only 1 piece of information. Technically, this is actually 3 unknowns and 2 pieces of information. There's another information here that says a squared plus b squared plus c squared can never be equal to 0. Okay, because I want this to be a non-zero vector. But instead of writing that out and making things even messier, I just say, okay, well, if it's a non-zero vector, let's just assume c is equal to 1, because at least one of the components of n has to be non-zero. Let's just set c equal to 1 and forget about it. And so this equation becomes this, and then you just get this relation between b and b and a. Aurora says, why are there infinitely many planes containing P0 and P1? Aren't they set points? Yes, P0 and P1 are set points, but there's not enough set points, right? In 3 dimensions, you need 3 set points, 3 fixed points to determine a plane. I mean, technically 3 points that are not lying on the same line to determine a point, but in general, 3 points that are distinct enough, they get you a plane that's unique. Just like in 2 dimensions, 2 distinct points get you a unique line through them. And 3 dimensions, you need 3 distinct points to get a plane through them. So in that sense, there's not enough information just between P0 and P1 to determine a plane. For between P0 and P1, there's certainly a line through it, but you could find infinitely many planes through 2 points. Okay, so maybe one way to see this is if you take your point 0 to be the origin and P1 to be the point 0, 0, 1, all right, in XYZ coordinates, then one plane through it might be the XZ plane, right? Just any plane that, just intersects this the central axis goes through the points 0, 0, 0 and 0, 0, 1. But the YZ plane also goes through it. And in fact, any single plane that you just rotate around the vertical axis also goes through those 2 points. So from those simple examples, you can sort of see why 2 points is not sufficient to fix a single plane. I should get on to doing the next part, which is finding distances. Let's completely reset for now, and we've now become somewhat acquainted with planes, right? We've done several horrible exercises. I've made several terrible mistakes, but we've fixed them, and hopefully you know something more about planes than you did previously. And so previously we knew how to calculate distances between geometric objects. We knew how to calculate distances between points and also distances between spheres, because we knew what spheres were, and you were able to calculate the closest distance between a sphere just by taking the distance between their centers and then subtracting off their radii, right? We did this in a previous lecture. And we also do, well, by sort of a similar ordeal, we knew the distance between points and spheres, right? So the distance between a point and a sphere, you take the distance between some point and then the center of a sphere and subtract off the radius of the sphere. And this is all geometrically makes some sense. But now, how do I? We now know a whole other family of objects, right? Now we have lines and planes. So how do we find the distances between such objects? So between lines, planes, and objects, and the shapes above. So that's a major section we have to do now. And so let's start with a line. Oh well, let's start off with the distance between a point and a plane, let's say. Okay. All right, so this really only makes sense when your point is not contained in the plane, right? Otherwise, if you're lying on the plane, then your distance between the plane and the point on the plane is 0. So the geometry of this looks like this. So here's your plane, here's a point P. And now I maybe suggestively sort of drew the situation out because you see that the distance I'm after is, if you drew a plumb line down and make a right angle, this length is going to be your distance. Okay. So how do I recover this distance, given the fact that if I have, let's say I have the coordinates of P, and I also have the equation of the plane. Does anyone have any suggestions on how I might do this? Right, so I certainly have a normal direction to this. The normal, I don't exactly know what the shadow of P is on this plane here, right? I don't really know where I am, in a sense, oriented with respect to the plane. I do know which direction up is everywhere. It's A, B, C. So I roughly know the direction normally to this. So what I want to do is project onto this normal direction. But what should I be projecting? What vector would I be projecting onto the normal? All right, so maybe I could just help myself out a bit. And if I take any other point here, let's say P that's on, let's say P on this plane, then I could draw a vector from P on this plane to P0, which is off this plane, right? So this is a vector P0, P. And if I could project this vector onto here, then that should get me the distance from P0 to this plane here, right? Hopefully this makes, this is a right angle triangle. It's just lying sort of sideways here. There's an angle here, and I want the length P0P onto D, or onto this this normal direction. All right, so by the absolute value of the scalar projection of the vector P0, P1 along the normal direction A, B, C. Right? In other words, you want this vector dotted with this vector, because dotted with the unit direction of this vector, right? Because remember, the dot product P0P against the vector in this direction, if it's a unit vector, is just the magnitude of P times cosine of this angle theta, which gets you this. Now, in general, this is not a unit vector. ABC is not a unit vector, and that's the vector so you got to normalize that, make it a unit vector. So you have to do P0P dotted with ABC over the square root of A squared plus B squared plus C squared, and that's precisely what the scalar projection of P0, P1 is, right? So recall from earlier that the scalar projection, I guess they call it component, right? The component of P0, P1 along N is equal to P0, P1 dotted with N over the magnitude of N, where I have theta there. So this is the same thing as magnitude P0, P1 against cosine theta, which is precisely what your distance is up to a sine. So the distance is equal to P0, your vector P0, P1 dotted with A, B, C over the square root of A squared plus B squared plus C squared. You want the absolute value of that. Oh, shoot. Yeah, horrible notation. Sorry, this is in chat. This is distance. Yeah, thanks in chat for that. All right, so, well, let's see if we could do an example here. find the distance between the plane P0 given to you by 2x plus 3y minus 1 z is equal to 1. So that's one plane. And I'm actually going to give you another plane, which is minus 4x minus 6x plus 2z is equal to 5. So I gave you a formula for between a point and a plane, but now I'm asking for the distance between two planes. So any suggestions on how I might do this? Also, how do I know that in this case, the distance between these planes is actually positive? Right, so Nimrat raises a good point. Check if they are parallel first. Actually, I don't know if you raised this point because I actually made this non-parallel. I think this is parallel. So I hope I did my math right. Right, so first, the normal vector to P0 is 2, 3, minus 1. And then what's the vector here? There's minus 4, minus 6, 2. All right, so observe that the normal to P1 is equal to 2, 3, minus 1. And then normal N2 to P2 is equal to, oh shoot, I call these P0 and P1. This is equal to minus 4, minus 6, plus 2. So it looks like they are parallel because, you know, this is, well, N1 is equal to minus 2 and 0, right? So they have not the exact same normal vectors, but the normal vectors are collinear. They're scalar multiples of each other. So what the situation I have here, say N0, is the following, right? So these are all parallel to each other, and there's a well-defined distance between them. So how might I find this distance between these two parallel planes, right? So I could adapt the situation from before. I could say, okay, I don't know, I don't have a formula, right, for a distance between two parallel planes, but I do know that, I mean, the distance is the same, right? If they're parallel planes, the distance is always gonna be constant. It doesn't really matter what, you know, where I am along these two planes. There's a well-defined shortest distance between them. By the way, what's the distance when two planes are not parallel? Or what happens when two planes are not parallel? Right, so two non-parallel planes must intersect somewhere. So the distance should be 0 because they always, at some point, they always intersect. So that's correct. This question only makes sense when they're parallel planes. Okay, so we have the suggestion, which is to pick any point. So you want to pick any point on one plane, then, you know, find distance between that point and the other plane. For example, I could pick a point here, P0, and then I just need to find what the distance from P0, little P0, is to the big plane P1, which we know how to do. Yeah, okay, so Myra says distances vary at different points. I should probably clarify this, yeah. Yeah, I should specify that the distances between planes should be, strictly speaking, it should be defined as the smallest distance between any 2 points on either plane. All right, so I take all my plane, my plane number 1 and plane number 2, and I get to pick any 2 points I want, one from one plane and the other from, you know, the second plane, and I look at all the possible distance between these two points, and the distance between 2 planes is defined to be the shortest distance between the combination of these points from plane 1 and plane 2. All right, just like the distance between spheres or distance between any 2 surfaces, it's basically you have the distance between any pair of points on these respective surfaces, and you just want to use as shorthand, you say the distance between 2 surfaces is the minimum of the distances between the possibilities of pairs of points. All right, so I hope that clarifies the question in chat, but that's a good point to be raised. When you say distance between anything that's not just 2 points, then you mean the smallest possible distance between the 2 objects. Okay, so to find the distance between this and the other plane, well, you just got to find, you know, a point P0. So what could P0 be in this case? So remember our equations are this and that. So does someone want to volunteer a point on the first plane? Okay, so we have 0, 1, 2, And 0, 1, 2 certainly satisfies this. I'm gonna put 0 here, then 1 and 2 and y and z get me 3 minus 2, right, equals 1. So P0 could be 0, 1, 2. And then does someone want to tell me how I might get a vector to help me out with this projection? What's another point, maybe on P1 that I need? So remember, to find the distance between 0, 1, 2 and the plane P1, I need to find a displacement vector of some sort. Should probably pick a point somewhere here and draw an arrow from P0 to that point. So on P1, right, I guess I didn't make this too easy for you guys, huh? So I could pick the point 0, 0. So I take a point on P1 here. Let's say P1 is, let's do 0, 0 and 5 halves. All right, so that certainly satisfies P1, the equation for the plane number 1. And so the vector is going to be equal to 0, minus 1, and 1 half, angle brackets here. And so the distance is going to be the absolute value, 0, minus 1, 1 half, dotted with the normal vector. And let's say, so this is P0 to P1. And the normal vectors are, well, they're multiples of each other. So it's 2, 3, minus 1. And you divide this by 2 squared plus root 4 plus 9 plus 1, right? So that's 14. And so I get what? So I get minus 3. Okay, so I get minus 3 minus a half. That's what? Minus 7 halves, root 14, something like that. So this is 7 over 2, root 14. Any questions here? Why did we not take N1? Well, the N1 and N2, they're the same, right? These are parallel planes, so it doesn't really matter if we take N1 or N2, or sorry, N0 or N1. They're just multiples of each other. I just took 2, 0, minus 1 because it's a lot better than minus 4, minus 6, plus 2. The reason it doesn't matter is because you're dividing out by the magnitude of the vector anyways. So it really doesn't matter which one you do. If I chose this instead, I would need to choose something worse. That would be like 16 plus 36 plus 4 on the bottom. That's 56 or something. It was root 56 and then some worse dot product on the top. So I just chose the one with the easier numbers here. And it's completely irrelevant because, like I said, you're just dotting with a unit vector here. So you rescale as necessary in this setup. All right, so here, that's the situation between a point and a plane, or sorry, 2 planes. Now, let's sort of up the dimensions a bit. So first of all, in this case, if you want the distance between planes and lines, once again, by distance between these 2 geometric objects, you want to find the distance is going to be the smallest distance between a pair of points, with the first point lying on a plane and the second point lying on a line. So when is this situation, well posed, in the sense that, when can you actually get an answer to this that is not always 0? All right, Raphael says same idea almost, right? So in what context would this distance actually be something positive? So a plane and a line that's normal to it certainly wouldn't work. What other situations, so if a plane, the distance between a plane and a line that is normal to the plane doesn't work because the line would intersect the plane. Right, so the only case where this makes sense is when you have a plane and a line that is parallel to it and is not contained within the plane, right? So this only makes sense where this is where this distance is positive, is when a plane is parallel to a line and doesn't contain it. All right, so in one of the situations above, we have that, right? You had a line here, and then you had a plane beneath it. Then once again, in this situation, you could really reduce it to some of the examples beforehand, which is if you have now a normal vector n. So what I could try is, where you have a point P0 here on this line. And then what you really want to do is you just, once again, you have a normal direction, and you have, you could choose any point you want on this line, and you could choose any point you want on this plane, and you want to do the correct projection, right? So the strategy here is, so pick any 2 points, construct the displacement vector, and then project along the normal direction. All right, let me see, question, same idea. Yeah, so it's the same idea as before. Before P0, P1. In the previous example, P0 is large P0 and P1 are planes, little P0 and P1 are points, even though my writing is pretty terrible. They look similar, but these are little p, and there's also the large uppercase ones. Okay, so we now know distance between planes and lines, because they're all pretty much the same situation as what we presented in the first case, which was distances between points and planes. All right, they all reduce to that case. So we finally now come to distances between lines, and now there are, there are a lot of different ways lines could occur in a sense in three-dimensional space, right? You now have two one-dimensional objects and three ambient dimensions. So this leftover dimension, in a sense, gives you a lot of freedom, and also makes sure that lines can actually behave in ways that you're not used to compared to lines in 2 dimensions, right? So in 2 dimensions, if I have lines that have different slopes, or in other words, if their direction vectors are different in 2 dimensions, do they intersect or do they not intersect in 2 dimensions? I have 2 lines with 2 different direction vectors, right? So they have to intersect, right? And if they have the same direction vector or direction vectors that are scalar multiples of each other, then they're going to be parallel. However, in the 3-dimensional case, that's no longer true. I could have direction vectors that even if they are the same, then if they're this, look, if they are different, then it's possible for them to not have an intersection, right? So they could have different direction vectors and not intersect, right? Because you have L1 here with the direction vector here, V1, and you could have L2 below it with direction vector V2. These are clearly not multiples of each other. They're pointing in different directions, but because L2 is by nature, in a sense, underneath L1, the way I drew it, then you're not going to have an intersection between these. Okay, so there's quite a different behaviors of L1 and L2 to consider, because in this situation, you could have 2 lines associated with 2 different vectors in a sense, and you want to find the shortest distance between them. Well, the shortest distance between them happens to be, if they don't intersect, they could, it's going to be a positive distance between them everywhere. So there's going to be a well-defined distance that's positive. And it's going to occur precisely when one of these vectors, one of these points is directly above the other, in a sense, right? The way I drew this. And the trick here is to find a way to find that distance, given the only data being that these 2 vectors are, pointing in different directions. Now, the other situation to consider is when you have parallel lines. In parallel lines, you could have, in 3-dimensional space, you have lines that are a constant distance from each other all the time. And then you have these 2 vectors that are essentially pointing in the same direction. They're scalar multiples of each other. And then you have to figure out how to solve this 2-dimensional, in essence, geometry question in 3 ambient dimensions to find the direction or the distance between them. All right, so in this case, these are called skew lines. All right, these are lines that are skew because they're not parallel to each other, but they also don't intersect. And because we're slightly out of time, at the start of next class, we'll look at how to find distances between skew lines. So these are lines that are non-parallel in 3 dimensions that do not intersect.